postdoc here at MIT, affiliated in various places, CSAIL, IDE, Fuchsia Tech, so on. She's presenting some work on when and how will we be automating specifically with data around computer vision and how it's going to affect jobs. So welcome, Wensu.
So thank you for having me in today's seminar, and thank you for Sunan's kind introduction. So today I'm presenting the working paper. It's a joint work with Aten, Kaiji, and Neil on the full versus partial automation. Basically try to give an economic analysis of how AI computer vision systems will affect jobs. And this is an ongoing work, so any of your feedback will be super helpful. And I'm delighted to share that another author of the paper, Aten, who is normally based in Switzerland, has joined us today. She will spend 1 week visiting us. So, like, if you ask some very difficult technical questions, I will direct to her. So, AI technologies such as ChatGPT and Vision Transformer, they are driving expectations for productivity growth, but at the same time, raising concerns about job displacement and predictions on the extent to which AI will replace human labor vary significantly among researchers, showing that this is a very complex question. You can see from Professor Asimoglu from Sloan, he made the prediction of 5% in a recent interview, but from the Bank of England, they make a prediction of 50% replacement rate. And given the US labor force of 160 million of them, so the differences in prediction actually have a very different implication. So our study will also give a prediction, but more importantly in this talk, I would like to discuss what factors should be considered when attempting to answer this question, and we will offer a framework to think about this question. So formally, for what share of tasks is it economically attractive to replace human workers with computer vision AI? And this paper focuses specifically on computer vision, which is a quite mature domain in AI. And in the future work, we plan to extend this to large language models. And we are now collecting data for the LLM research. So before we go into details, I would like to say something about what we are modeling and what we are not. So we are discussing replacing human labor, which is, we call it a Turing trap job automation, rather than creation of new products, new services, or new tasks. Because the uncertainty surrounding the latter is even greater. So we will confine our analysis to the first part here. So there are much work has been done on the impact of AI on jobs, often using task-based frameworks, but some of them also use like abilities, skills as the connecting factor. And this means that viewing an occupation as a collection of tasks and analyzing how new technology would impact these tasks. But however, among these works, only very recently, our paper, the Svanberg 2024, explored the economic attractiveness of AI. So before that, like seldom the literature will consider the economic feasibility, but only focus on the technical feasibility. But we will consider also the economic attractiveness. So in addition to building on the concept of economic attractiveness from Svanberg 2024, we introduced the idea of partial automation, where human and AI can cooperate at task level, instead of a world where tasks being entirely completed by human or entirely automated by AI. So like many other studies, we use the ONET tasks framework. So ONET is a database maintained by the US Department of Labor that breaks down each occupation into tasks. For example, software developers are divided into 19 tasks. And when people say about partial automation, maybe they will first think of a scenario where some tasks are automated and some tasks are still performed by human. But we actually go into a more detailed level, and we will focus on the partial automation at the task level, which means that we assess how humans and AI can collaborate to complete a task, measuring how much of a task progress can be achieved by AI and what could be the remainder will be achieved by human. But of course, incorporating the task level automation rate with the ONET task system, we will be able to also calculate the occupation level automation rate. So to give an example of partial automation, so IFFCO Tokyo is an Indo-Japanese insurance company, and they were considering to use AI system to automate the insurance claims processing, and then a full automation case for this task would be a consumer to take pictures of the car, the damaged car, and then AI will process the claim entirely. That's an example of full automation. But in fact, what happened, their decision is that they built a partial automation system where the AI only previews the claims, but human will confirm and finalize it. So full automation in this case is not feasible because AI cannot meet the required accuracy for this task to completely take over this task. And fully automating it would be prohibitively expensive. However, even partial automation can help a lot, can reduce the claim processing time from an average of 5 hours to only 30 minutes. So this is an example of where partial automation is more attractive than full automation, and why partial automation probably will be a more common case than full automation. So another example is from the ONET database. For example, podiatrists with the task of diagnosing diseases from X-rays images. Okay, then in this case, the AI's role can be identifying potential symptoms or diseases from the X-ray, but not deciding this is the exact problem. So it narrowed down to a short list, and then the doctor's role will be to review the AI-generated list suggestions and make their diagnosis and to develop treatment plans. Okay, now let's reconsider this question from a perspective of computer sciences. So this is a classic computer vision classification task where the input is an image representing a disease or a case of no disease. So in computer vision classification tasks, a very important concept is the number of classes. In this case, if there are 400 diseases podiatrists should be able to diagnose, then the number of classes is 400. So then the output of these tasks is to identify the correct disease from these 400 classes. So a full automation would be an AI system that selects the correct class with high accuracy. But partial automation would mean that actually it would give a short list of the potential diseases. Maybe it will also give a confidence score like 88% is this is the stress fracture, and like 12% is other disease. And then the doctor will do the final judgment. So in this case, you will see that essentially the AI system is helping to simplify this problem. So another example from the ONET system is that for the occupation of weighers, measures, checkers, and samplers record keeping, the task is to compare the product labels to ensure that there are no mistakes. So the AI's role could be detecting potential mistakes for all those, a large amount of cases, and then a human's role can validate the AI flagged issues. So it would save humans time from reviewing all the cases. So now we understand how human and AI collaborate at the task level. So we must quantify partial automation, and this requires addressing several technical questions, including how can the extent of partial automation be rigorously identified and quantified? And what are the economic benefits and costs of implementing AI-driven partial automation? And what decision variables should be considered to achieve economically optimal outcomes? So to answer the questions, we build a framework that relies on a key concept, which is called the required accuracy. So the required accuracy is highly related to the efforts needed to complete a task, whether by humans or AI, and very significant. So the required accuracy is the minimum accuracy needed for tasks. So it will denote the effort needed to complete a task, and it will vary significantly across tasks. So I give two examples here. For airline pilots inspecting aircraft defects, this task has very high required accuracy. And compared with label comparison task is with lower required accuracy. We can understand that why the first one will have high accuracy, because of the consequence of making mistakes and the effort it needs to check the list. And then also for the second task, because the number of classes, the number of products could be very large. So that also gives the reason why we allow for rooms for more mistakes, higher error rate. So again, using the pediatrics example, so when in the case the task is performed by humans, the typical accuracy is 97.8%. That's from our survey. We will talk about it later. So note that humans also make mistakes. So we are requiring a doctor to do this job does not mean that he's 100% correct. So completing the task can be seen as a process of improving the accuracy from a random guess accuracy to the required accuracy. So a random guess accuracy, you can imagine it as a case of the doctor is making decision blindfolded without looking at any image, any information. So maybe like a rational choice is to guess the most frequently happen case. So, okay, now assume that an AI system can achieve 98% accuracy. So this actually exceeds the required accuracy, which is the human accuracy. So we say that in this case, AI can fully automate this task. But imagine in a scenario where AI only achieves 90% accuracy. So then human involvement is needed to improve the accuracy from 90% to the required level. So now the real challenge for us is not the technical feasibility of obtaining a model that's 90% accurate or 98% accurate. Because given sufficient resources for data and compute, and we keep scaling the AI models, higher accuracy can be achieved. But of course, potentially with higher cost. Like, of course, with higher cost, but 98% must be very high cost. So the key question now is, of all these models with different levels of accuracies available, but just a matter of increasing cost to build a better one, how do we select an optimal model, an optimal model accuracy, considering both cost and benefits? So whether it's partial automation and full automation is actually a choice, but not entirely linked to whether it's technically feasible to do so.
Sorry, Sam, go for it. I think one issue in this broad literature more generally is this notion of the moving target. The models are moving quickly in terms of their accuracy and performance. the cost of the models is also moving quickly
Yes.
in terms of the required financial inputs, whether it's token costs or data costs or whatever. And so we're trying to make predictions about labor, automation, and substitution, not today, but in the future.
Yes.
So is there some requirement for forecasting costs, accuracy, model accuracy over time in order to do this right?
Yes, I think that's a very important consideration. Like currently today what I'm presenting is a static model, like just build a method. But with the cost given from our previous case study, from our investigation, but then like in the November 2024 work, we also do make assumptions about how the cost of building AI system decrease over time, and we adjust the predictions according to different speeds of costs going down. And then also, even for a given fine-tuned CV model, we need to retrain it to adjust for the problem called data drifting. Like there will be new data, new cases, new classes, so we need to retrain the model repetitively. So you can see that in our data structure, the costs not only include the cost of building the AI system, but to maintaining it and to retraining it. And we estimate a lifespan of the product, and within the product, what is the retraining cost, we will calculate the expected value of those.
So you said earlier that like the cost of producing a better AI system is going down, but wouldn't you be expecting a higher cost for improving an AI system from like 19 to 9%, 99.9% versus going from 19% to 99%? Shouldn't it be increasing?
Yes, the cost from 90% to 98% of course will be increasing, but over time this cost will decrease over time. But like to achieve a 90% model, it will be cheaper than to achieve a 98%.
I think that's what that means by moving target, right? Because the over time, the sort of amortization of the cost could be just 1 year, or it could be 10 years, and that makes a huge difference for the cost of the model. Right?
Yes. That depends on like how fast we should just adjust the model, and then that also depends on the improvement of the foundation model. Because like what we are now talking about is like if we take a foundation model, a CV foundation model, if we fine tune it to an application, what will be the cost? But of course, if the foundation model's performance increases, the cost of fine tuning it to require a target's accuracy will also decrease. And as the requirements of people's like the expectation to AI increases over time, like the required accuracy will also may increase over time. So yeah, I think that was a very good addition. I don't know if that answers your question.
I'm curious later to see what the cost modeling looks like. I think the cost modeling depends on what people expect from their AI systems, right?
Yes.
And as people expect more and more and more quickly,
yes.
It's almost like the cost goes up exponentially faster, as opposed to like, logarithmic.
Yes. So we are now making the assumption that like the required accuracy is the humans currently performing accuracy, the human accuracy. But here we have a concept of AI accuracy, and this is a choice, not a nature of the task. Like the required accuracy is the nature of the task, but over time the AI accuracy that we choose may increase over time, right?
Yeah, I think maybe I can add on this point. So for your question about how fast the model can run, it probably depends on two sides. One is the computational power. The second will be your algorithm of your model, how fast you can run to get the results. Yeah, that's
Oh, I guess I didn't mean by speed of compute. I just mean like the speed of improvement. Because you might go from 90% this year to expecting 95%, and then 99%, and then 99%, and it's like getting harder and harder.
Yes.
Moving goalposts.
So this framework is actually flexible for those changes. I think you get a better sense later. So like to answer the question of okay, what we left. So okay, so we try to answer the questions of how to select the optimal model accuracy, the AI accuracy. So to answer this question, we need to break it down into 3 steps. The first step is when the model achieves intermediate accuracy below the required level, how much labor can it substitute? And this captures the benefit sides of the AI automation or the demand side. And then the second is the cost side of training and deploying an AI model. So we construct the supply curve for the AI quality. And once we have the demand and the supply, we just find the equilibrium, the optimal AI accuracy, the optimal performance, model performance level. So like returning to this example again, so here, if the AI accuracy is like 90%, does it mean that it has completed 90% of the tasks? So like if AI's accuracy lies between the lies in the very middle point of the random guess accuracy and the required accuracy, does it save just that exactly half of the labor?
Not
No.
really, right? Because like it could be the hardest cases that you're missing.
Yes.
It could be the highest cost.
Yes, like very intuitively, the answer is no, right? Because accuracy improvements are not linearly correlated with labor. But luckily, we have some theoretical basis to address this problem. So the psychology literature provides evidence that not accuracy, but entropy is a linear measure of labor. So task entropy is a concept from information theory, measures the uncertainty or complexity of a classification task. So the amount of human labor required is proportional to the reduction in entropy during the process of completing the task. So this is based on the series work by Haymond and Siebel and Hugendorf. And then a closer look shows that entropy and accuracy have a very close one-to-one mapping, actually. So improving AI accuracy essentially reduces the task entropy. In computer science, cross-entropy loss and accuracy are common performance metrics that reported for AI models. So for this study, we actually fine-tuned a computer vision model and plotted the relationship between accuracy and cross-entropy loss. And this relationship also varies by the number of class. So recall that the number of class is also a metric to define the difficulty level of the classification problem. So then we estimated these curves for different number of classes. So we can see that there is the slope of these curves decreasing when it close to 100% accuracy, close to the required entropy. That means that like improving the very last bit of accuracy actually requires more work. Like improving from 40% to 50% is easier than improving from 80% to 90%, if that makes sense. So using the one-to-one mapping between accuracy and entropy, we can now convert random accuracy to task entropy, which represent the difficulty of a classification task. And this table down here shows the comparison with 2 classification tasks. And you can see what the easy one looks like and what the difficult one looks like. And then similarly, required accuracy can be translated into required entropy. And an AI model's accuracy corresponds to its cross-entropy loss. So in this sense, cross-entropy loss and entropy, they are 2 interchangeable concepts. They are basically the same thing. So recall in the pediatrics example, we say that AI narrowed down the choices from 400 to 2. So which is equivalent to reducing the task entropy from the task entropy level of 400 to the cross entropy loss level for the human.
Are the classes are uniformly weighted? Is that
Not necessarily. There could be different distribution of the probability of each classes. So if it's evenly distributed, that is the hardest case to guess. But if some classes with higher possibility then the accuracy is actually higher. It's easier to guess.
I
Right?
wasn't thinking about the weighting of the distribution of instances of each class, but sort of the distribution of the importance of correctly categorizing one class versus another.
Yes, yes, that's an important aspect. So, and that's also an aspect that vary case by case. So that's why this kind of work is challenging because we are talking about different classification problems in different jobs. So this is only a way to simplify to try to capture the key concepts, but there is a lot of things to consider when you want to apply it to an actual business, an actual case.
So just an example, I guess, you could be an engineer at Boeing and look at a piece, and then the number of classes, whether it's faulty or not, it's just 2 classes. But
Yes.
the complexity is very high, right? Because if you were to mistakenly misclassify,
Yes.
that's a huge cost to Boeing and to the passengers. So in that sense, this criteria is not quite capturing that. I think.
But that is captured in the required accuracy, right?
Mhm.
And it also captured, you later see the benefit consists not only the proportion of entropy reduction, but also related to the wage of the people who are doing this task. If this is important, it will usually given to a person who is like high paid with expertise and ability to ensure this is done correctly. So yes.
In the distribution of the instances of each class comes into account where here? So the assumption that each class has an equal probability, if this is something you relax later or?
Let me think.
I mean, I'm just thinking about.
This is just an assumption for this table.
Right.
We are not using this assumption in our
Okay.
analysis.
Because in Hung Yi's example, you might have 2 classes of faulty or not. You might have 99.9% not faulty, but it's that 0.1% that
That
you really want to
really
be able
matters.
to identify with great accuracy.
Yes, yes.
Because my model could just pick not faulty, could just be
Yes.
set to guess not faulty for everything and have a
Right,
very high
99%
accuracy.
Yes, but that is also captured by the task entropy, right? So if like 99% of the case is not faulty, right? Then the task entropy will be very close to the required entropy in this case. So the improvement the proportion of improvement could still be captured by the distance between the required entropy and the task entropy. So the case you described is like the random guess accuracy is very high, right? But the required accuracy is even higher, right?
Well, I mean, I'm just thinking through your example, and forgive me because I'm
Yeah.
just thinking about it on the fly, but 99.9% of parts in the Boeing plane are not faulty. You really want to know the 0.1%. The task entropy there is very similar to the required accuracy. You want 99.9% required accuracy. 99.9% of the parts are not faulty. But the key is discerning between the two, right? So does that example really demonstrate what you're trying to say or sort of demonstrate the opposite of what you're trying to say? I'm not fully understanding this task entropy is not the same as required entropy because it seems like in that example, the task entropy is high. The required accuracy also very high. But that doesn't make the task less complex or the accuracy, the importance of the accuracy of the model less important.
You're right. It's not less important.
It's like a catastrophic failure situation. That's why I asked before about not just the distribution over the classes of the instances, but the distribution of weights over things,
Different classes.
importance.
The importance of making the
Yeah.
decisions.
Because it doesn't consider that your false negatives and false positives.
Right.
Yes.
And disutilities of each of those.
Right.
Yes.
Misclassifications.
Right.
Here, everything's treated uniformly, right?
Right. And in
Yes.
fact, in this example, the false positives are almost meaningless. Like they have zero cost to me.
Yes.
The false negatives have very high costs.
Yes.
Yeah.
Yes, I agree. And so I remember a friend of mine told me that he's in the compliance department of a bank in Hong Kong, and then they are relying on the AI system to do the money laundering detection. So maybe that is also an example of like a false alarm is zero cost, but a missed alarm is very important. So what they did is just they run the AI model multiple times and they try different prompts to try to capture all the cases. But of course, the reason why there's partial automation is there's some part of the aspect or nature of the task that cannot be fully completed by AI. So yes, so we need to discuss it case by case.
I just want a clarification. Is there relations between the number of classes and the task entropy or task? Like, does the number of classes determine the complexity and the task entropy? Does it have like causal relationship?
Yes, task entropy highly depends on the number of classes.
So
The
more-
higher the number of classes, the higher entropy, the more complicated the task.
Okay.
Okay, so can I move forward? Any other questions? So now let's revisit the task completion process. Now using entropy instead of accuracy. So this is uniform according to entropy now. So based on the Hackman law, labor time is proportional to the entropy, so that the distance between required entropy and task entropy represent the time needed to complete the task without AI. And then the distance between cross entropy loss and required entropy reflects the time needed with AI's assistance. So this allows us to define the automation rate based on task entropy, required entropy, and cost and cross entropy loss. Yes. So to estimate these variables, now we conducted an online survey in November of last year. So we have about 3,778 participants across 263 occupations, and they answered questions about 420 vision-related tasks. So the survey questions include what is the required accuracy and what is the random guess accuracy for this task. And we also collect data on task level wages and employment from other sources. So then with these variables, we can formally calculate the benefits of improving AI accuracy, but just in a sense of labor replacement, not accounting for the benefit that Sinan mentioned is very important, like value creation. We're not capturing that part just for automation. So then it's important to say that demand is defined in terms of quality, not quantity. We are not talking about how many AI models to create. The entire framework assumes that the goal is to build one single model for one single task, with costs and benefits increasing alongside with quality. Okay, now we finish answering the first question. We go to the second question, which is the supply side. So having addressed.
Sorry, just going back to that prolific study that you did you do any kind of validation during that study to ensure that sort of like there is sort of this like linear relationship that you mentioned between like sort of entropy saved and amount of labor, where it's sort of like, right, did you like do sort of like a control versus a treatment where it's like you could quantify that, like in the case where people didn't do AI, like sort of the entropy of that task that they saved was like linear in labor? Because
So for the computer vision survey, we didn't do that verification, but we are actually able to get to that question in the LLM version survey. We are moving it to an LLM version survey, where we actually present some AI generative work to the respondents to ask them, if you are going to do this task from scratch, how much time you will need to complete this task, and with the help of AI, how much time it will save you. to reach the required standard.
So for the recruitment of these participants, did you basically just like screen them out based on whether or not you fulfill an occupational bucket? Because you said you were able to get participants across 260 occupations, and I'm surprised because Prolific I thought was a lot narrower of a crowdsourcing platform than.
So you mean the
Yeah,
we
for these
cannot get the full
3,700.
range of the occupations.
Right.
So we require the respondents to have at least 2 years of work experience and they are familiar with the occupations. So it does not require them to actually work in this occupation, but they can be familiar with the occupation. For example, if they are have families that work as this job,
Yeah.
and then yes.
So I'm just thinking in terms of verification purposes, like is a respondent just getting an email and you would then reply with what occupation? How do you verify they're replying with the right
So
occupation?
we build a navigation system using Qualtrics. So in the Prolific recruitment page, we say that okay, we need respondents who are familiar with this list of occupation.
Yeah.
All the occupation are corresponding to about 2 vision tasks, and then we will let them to choose which occupation you are familiar with. And then, so if they choose, okay, I'm familiar with this occupation, but then we show the tasks, show the description of the task, they say, I'm not familiar with the task, they can have the option to skip the task, so they will not answer about the task. We ensure that they're familiar with the task before they proceed to answer the questions about the tasks.
Right, but like that's asking for like self-reported familiarity, right? Like,
Yes.
With 10 responses, let's say 3 of them which completely lying, you would have like a big noise injection in your sample, right?
Yes,
Like what is the incentive, I guess, to report truthfully whether or not you're familiar with the task, given the incentive in Prolific is to just earn money quickly and just like respond to things.
Yes, I think maybe that's one caveat that we cannot overcome with like this broad range of occupations. Like I admit that there are some occupations that is more difficult to get respondents than others.
Like I'll be surprised if there are lots of radiologists on Prolific, right? And that would be a surprising fact for me to find out.
A lot of what?
Radiologists.
Radiologists.
Right, like they're not searching Prolific to answer questions, I think.
Yes.
I think we should let you go on because I'm very curious as to what the predictions say.
And okay, so again, we are moving to the second part, like how do we model AI accuracies apply, and how do we calculate the cost of building a model with a given AI accuracy? So it turns out that in different domains, AI performance correlates predictably with certain input factors. And these relationships are described by the body of literature called the scaling law literature. And then this chart shows examples of scaling law across domains where the vertical axis represents the cross-entropy loss. So for computer vision model performance, 3 factors are particularly influential. First is the data, it's the number of training images. So more data generally leads to better performance. The second is the model size, the number of parameters in the AI model. So larger models typically perform better. And the third is training steps, the number of gradient descent steps performed. So we estimate scaling law useful directly as a production function. So we fine-tuned a swing transformer vision model across 80 different configurations and recording performance under various settings. So based on this data, this is the estimated scaling law based on our experiments. So we use this as a production function. And the next, we examine the costs associated with increasing these inputs. So this means that how does building an AI model's cost scale with data, model size, and training steps. We have data for the cost of collecting image data, the cost of compute, and what are the fixed costs of submitting paying the engineering team, and what are the variable costs. So for this part, we adopted the cost structure from November 2024. Okay, now we have both the cost function and the production function. Then the problem becomes a very classic economic optimization question. So that is the target entropy. We can determine the optimal inputs and derive the marginal cost curve, which is essentially the supply curve. So we finished the first and second part. Now we
And
go
just to recap, the output here is accuracy.
yes, we formulated to entropy, so interchangeable, because there is a mapping relationship.
Okay.
I'm sorry, this is Michael from just watching
Yes.
this. May I ask a hopefully non too ignorant question, given how you've shown this circle and this cost minimization
Yes.
question?
Yes.
As one looks at the history of economics and how things are manufactured or get better, the phrase learning curve becomes very important. So there's a learning curve. And workforces learn how to become more accurate, more efficient, whether you're Boeing or McDonnell Douglas. The thing that I'm not seeing or hearing here, maybe it's implicit or endogenous in what you're sharing, is yes, you're training these models, but once they are deployed, are these static? They no longer learn. It's simply the implementation of an algorithm. Or do, in fact, like humans on the factory floor, do they learn to get better? I would just like you to clarify that confusion for me. My thanks and apologies.
Yes. So if we look at this cost structure, there are in the performance-dependent cost, there is a sector that is retraining cost. So we actually assume a lifespan of these AI models, and then we account for the retraining cost over time. Does that answer your question?
No, it does not, because you're giving me the cost of training,
yes.
but in the same way we have people on the factory floor who get paid a salary. But the economic history is that there are indeed learning curves, i.e. people become better and more efficient over time. I would have thought that the argument would be that AI itself, unlike classic algorithms, learn to get better and more efficient over time. So in fact, they learn. So it is not just we train them and we put that learning on the factory floor. It is in the act of deployment, it learns to get better. That's the confusion that I have in this presentation here.
This is the same question that I started with, at least in part. So
okay,
part of my first question.
That just underscores how little I understood, Sinan.
No, it was the same question, except in addition to that, there's a change in cost, right? But he's right. I mean, it's, you know, today's model is not tomorrow's model.
Yes. Yes, there's a lot of consider, including the algorithm improvements and like so do you think it would be a good way to model it as the decreasing of the cost in constructing the model?
I don't know what the right forecasting model is, but somehow I think this would be like having a forecasting component to this.
Yes.
Forecasting the cost.
I agree. My weasel suggestion would be that you take historic learning curve data and assume it in certain kinds of forecast scenarios and see what kind of efficiencies and savings and productivity emerge.
Yes.
At the same time, though, I feel like this is a good start. You know, you start with this, and then it's, I wouldn't say trivial, but it's simpler to then add a forecasting component to this, and it would plug right into the framework that you're already explaining.
Yes. And then even with the prediction of our current model, we might give a prediction of how much could be economically attractive to be automated. But people are not going to adopt the model right away because there's also a process of information technology diffusion for people to learn about the AI technologies. So this is from a standing point of we know about the technology. We know that for some areas it's feasible to automate, but there's time needed for this information to express. And Okay, so then like the final part of this framework is to the interaction of the supply and demand curve, and we determine the optimal level of the model's performance, which is represented by cross entropy or accuracy. So now we finished the methodology part. Let's go to look at some results. So like this is an example of what currently we can do is that if we input the total employment of a given occupation and the average wage of that occupation and the time proportion on the tasks that make up this occupation, and then also we label the number of classes for that occupation, and we get the required accuracy from the survey, then we will be able to draw the marginal benefit and marginal cost curve and to predict optimal AI accuracy and the automation rate based on the entropy method. So in this example, it only achieves 43% accuracy, which means that there may be a lot of false alarms, right? But then it can save 60% of this employee's time on performing this task. So one thing I would like to compare is that an important concept in here is the deployment scale. It's like, it means that once a model is built, at what scale it is deployed. So if the deployment scale is at firm level, a firm develops its own model and deploy it within the firm, then we assume that all the employees in these firms that doing this task will use this AI tool. But if this model is developed by a third-party tech firm or like you can say AI platform provider, then and it has the ability to be shared with all the employees in an industry, then it's a different story. The deployment scale is much larger, which means that the benefit is much higher, and so that we can amortize the high fixed cost of developing AI models. So better models with high accuracy and higher automation rate will be developed with a larger deployment scale. So in this example, they are the same task, but just assumption of different deployment scale. On the left-hand side is across the economy, the right-hand side is across an industry. So, and also the difficulty level of the task. Like on the left-hand side, we have a quite difficult task with the number of classes of 540, and the left-hand side, we have a simpler class, right? So then the obtained AI accuracy is much lower on the left-hand side, and then it's only partial automation, but on the right-hand side, we have full automation. So, like,
this right-hand side example goes right to the conversation we were having before. Two classes where the importance of getting it right is high. In one of those two classes, AI accuracy of 93 would predict a 0% automation. Right? I'm not going to accept an AI model that gets 93% accuracy where when it gets it wrong, it's a catastrophic failure.
But the argument is that the human accuracy is only is 93. It's reported as 93. It's
okay.
not like so maybe for this occupation is actually acceptable at a 93 accuracy. So but if like it's that important, like it requires 99%, then maybe it's not for automation.
Okay.
So
so AI accuracy here is the required accuracy. Because
so
what you labeled in the previous slides was AI accuracy was one thing.
Yes.
The required accuracy was something else.
Yes, but in this particular case, because it's full automation, so it means that the AI accuracy actually exceeds the required accuracy. So like you said, if we got the task level automation rate, we will be able to aggregate it at occupation level. So this is the outcome of the estimated share of compensation that could be automated by computer vision systems at different deployment scales. So if we, so for full automation, if with the deployment at the firm level, it can automate about 23% of all the computer vision tasks we identified. But with partial automation, this rate go up to over about 50%.
So just to be clear, that last bar means that you are predicting 70% for full automation in the US economy?
So that is, like, it's very important to explain what it means. It means that if an AI, once a model is developed, and because the nature of this task is quite universal across different industries, and it can be used by all the employees doing this task for the US economy.
Okay.
So then it will be, full automation will be about 70%. So actually maybe the firm level is a more reasonable assumption that assuming a system can only be used at the firm, within a firm. So the horizontal axis here is the deployment scale.
Okay, and we're talking about computer vision, et cetera, et cetera. So this is a
Yes.
smaller piece of the much larger labor
Yes.
force. Yeah.
Yes, so here the 100% is 100% of all the computer vision
Right.
task compensation values.
Got it.
So like,
How do you define a partial automation rate? Is that anything less than full? You call it partial?
less than full is partial.
Okay, so even if it's 99% automation rate, you'd still call it partial.
Yes, like we have a distribution of what is the partial automation rate across, yes, different counts of the models.
But why don't you put a threshold of this partial automation rate? Because 99% and full, it's quite kind of similar, right? But 20% and 100% is kind of very different.
Well, we can adjust for that definition and create another graph for
Okay,
that.
I think that would be helpful because looking at that, it's like,
Yes.
I think some of them are in the gray area.
Yes, and you're right. And you say actually a very significant part, many cases are falling to the above 90% automation scenario that you described.
Right,
So
but they're not
we-
100%. So
Not 100%, yes.
yeah.
And then we calculate this automation rate for all the identified occupations. So if we focusing on the top ones, we can see the top occupations that with the highest potential to be automated by AI. So the red part is the fraction that is by full automation. The blue part is the part by partial automation. And you can see that transportation and security screeners, they have a very high proportion of tasks that is vision. So that naturally makes it easy to be automated. But also there are also other occupations that's with a high fraction of CV tasks, but some tasks are not feasible to be automated. So it varies case by case, depending on task characteristics. Have questions?
Yeah, sorry, I'm just looking at this list, and I guess intuitively, I'm wondering what part of a chef or head cook's job would be something that could be automated by computer vision?
To check the quality of the food, actually.
To check the quality of the food.
Yes, like by looking at it to see whether it's it cannot be used is like
Rotten.
yes, it's rotten. Yes.
And also like, this is, and also the lifeguard, ski patrol and so on, right? So like, maybe 99% of their job, let's say we just give you your assumption, 99% of their job is to look and see if anyone is, like fallen down on the ski slope or is holding their leg with a broken leg. But like that 1% where they go and save the person is actually their job, right?
Yes.
It's not, and the combination of the two is the job. Like you
Yes.
can't like take part of it and give it to a computer. The other part of this that's a little not quite fitting for me is that while it is theoretically possible to show a computer images of a ski slope,
For what?
of a ski slope, the ski patrol, right? That's your second, your
Yes.
third, right? Putting a computer in a live scenario looking at a ski slope And then being able to go there and do something about it is a very different thing, right? So you can imagine there's like cameras all over the ski slope, and then there's like a headquarters down at the base lodge. And they say, oh, there's a guy up there with a, but then that's when you need the ski patrol, is they
Yes.
gotta go up there and do something, you know?
Yes, yes.
But you can't automate, you can't, how do you say, you can't fire any number of ski patrol,
Yes.
right?
And that's why, like, while technologies are changing, the way of people how to work with technologies are also changing. And actually, we are relying on the ONET that system, the ONET definition updating, like what are the tasks that consist of their jobs because of these technical changes, right? So like that is the one thing we specify at the beginning, like because of the limitation of the ability to access what is the new processes, new business processes, new product, new services that are created. We're only talking about the automation part. And there are some tasks that naturally combined with like physical execution of the task.
I think a lot of them, and I think you should think a little bit about this notion of decomposability of these tasks. Is it really true that I can take an occupation and I can look at the list of the tasks and I can think about them in the context of the occupation independently? So for example, I could say, let me think about Roger Federer Wimbledon championship tasks, okay? A lot of his tasks is seeing the ball, right? Knowing if it's going in or out, but he has to combine that with a physical task at the same time.
Yes.
And I couldn't partially automate Roger Federer with a very high accuracy machine that could know whether the ball is going to land in a certain place.
Yes.
It has to be the combination of the physical action and the computer vision. And those two things in Roger Federer's case are not decomposable.
Yes, but for that part, I actually quite trust the definition of the ONET system because the way that they define the task, they also consider the separability. So they would not separate these two parts, these two tasks.
And if that's the case, then a lot of what I'm seeing on this table isn't making sense. Right, so then it's not a matter of ONET and the separability problem. It's a matter of applying ONET, as you have here, not capturing whether some tasks are separable or not. Because, for example, the lifeguards, the ski patrol, and the example of the chef are situations in which those computer vision tasks and other tasks within their occupation should be better captured as non-separable here.
Yes. So I think maybe the next step is I look closer into this explanation and see the seemingly weird task, what occupation, why they're happening in this way. And actually there is one example that is about athletes. Like actually a large proportion of the athletes' work are predicted to can be automated. But that is because actually I don't remember, 20% or 30% of the athletes' work is to analyze the previous games, to analyze the strategies, so that that part could be automated by CV systems. And so maybe there are some occupations, seemingly it's that you only focus on the major jobs, major tasks, but in ONET it defines many of other tasks that maybe not the major tasks, but consist a lot of their jobs, and they spend a lot of time doing those. So maybe if we break it down to those tasks, you will see why.
But you see the separability problem,
Yes,
right?
yes.
When you say the athlete, okay, I'm thinking about the quarterback,
Yeah.
right? Who's getting ready for the game on Saturday. And I've got a computer vision model that can analyze all the past plays of the opposing offenses and defenses, right? But it does not help me at all unless I can put that into the brain of the quarterback that's going to take the field on Saturday.
Yes.
It's not separable. You cannot automate that part. You have to put you have to put it in Tom Brady's brain for it to matter.
Yes. So yeah, maybe we can also play around with the definition of partial automation, like what it means, like to bring in more richer content in this concept.
I think you're going to get a lot of mileage out of thinking more about separability and how you're applying separability to this table.
Yes.
It could be that ONET has separability scores, which is great,
right? It could say, like, these tasks are or are not separable. Then maybe it's an issue of how that's being baked into what you're doing, which is also really good news for you, because that means that you can adjust to account for that better, right? Because I do think that when you put this table up, you're gonna get some pushback.
I see.
And when people see Chef up there at number
I see.
4, they're gonna say, I don't understand how I can automate Chef through computer vision.
Just have a question on your part. So you mean if it's partial automation, then it must be separable.
Yeah, I think
It's
that
like
in order to make good assumptions about partial automation, then I have to be able to do the automatable parts of the job separately. And that should not reduce my ability to do the other parts of the job. Like
So
the-
it might have less
like-
classes than the full automation jobs.
I think that the classes are about the different things that the model can predict, the number of different options the model has to predict. Like, is it one of these 500 labels, or is it broken or not broken, like a binary label? Those are the classes. But in an occupation like quarterback, you have lots of tasks, okay? And task 1 is to study the offense, or the defense that you're gonna face on Saturday. And I can automate that with computer vision very well, because I can see all the X's and O's, I can crunch lots of data. But unless I can put that into the muscle reflexes of myself on Saturday, it's meaningless, almost meaningless. Maybe it could be a tool, like an assisted tool. Tom Brady can look at the computer output, but eventually there is not complete separability of those tasks.
I think there's one distinction here I want to make. So when we say partial automation, we don't mean that we are replacing these people, right? So of
No, I
course,
know.
some of the tasks can be assisted with, so it saves my time, and that's the key point. So although I cannot completely replace this person, and this task is entangled with other tasks, but as long as it provides some value to reduce my time of doing this task, then that's how we define the partial automation in here.
I see that. I see that completely. I think it's important to understand the extent to which the ability for a computer to do task 1 actually affects tasks 2, 3, 4, and 5, in order to accurately sort of account for task 1. Just because a computer can do it well and economically efficiently and accurately does not mean that that task should be automated, because it may have very complex spillovers onto tasks 2 and 3 and 4, where tasks 2 and 3 and 4 suffer when the person or the entity executing those tasks is not also doing task 1 anymore, right?
Yeah, for that part, I agree.
Imagine, like a computer vision model is better at seeing the tennis court than Roger Federer. Say I develop a model. Now imagine having Roger Federer rely on that model and then play the match blindfolded. That's the problem. They're just too closely intertwined in the moment of execution, right?
I have a separate point. So if you go back to your slide about the optimization problem that each firm is solving, I think it's like minimizing some cost subject to like a baseline level of like entropy that corresponds to like the minimum task complexity. Yeah,
This one, yes.
this slide. Have you considered like looking at results of what happened if you like solved the dual of this instead? So if they're trying to maximize sort of like the amount of uncertainty they could explain subject to some cost, because like I think a very interesting alternate spin of that graph is sort of like, how well can we improve classification accuracy across different sectors while like retaining sort of like similar costs to before, like with sort of advances in AI. right? It also kind of seems more commensurate with reality in some industries because, like, for example, in the TSA example, like, right, if the TSA has like a way of better screening for like, dangerous objects at airport checkpoints, they're not going to be like, okay, I'm satisfied with the current baseline level of misclassification we have. Presumably they try to like increase the level of accuracy that they have and like move that baseline. So it'd be interesting to see like, if we adopt AI in certain industries, how much better we would get at classifying certain things.
Yes. Yeah, I think like we can talk more about it, like the details of how to do that afterwards.
So very interesting. Couple thoughts, right? I don't know if this is within the confines of the study, but when you use the example of the doctor and using the X-ray, two things that come to mind. One is, what's the distribution of the human accuracy? Because you can have a good doctor and a bad doctor.
Yeah.
Good doctor can miss it. Or you can have a good doctor having a bad day, right?
Yes.
And how's that important? So I assume that, when you incorporate a computer vision model, the variability is reduced, or at least you're always getting that accuracy, right? So
Not necessary.
not necessarily,
Like,
okay.
yes.
But is the variability also reduced then? Or the distribution are you getting consistently 93% accuracy?
Mhm.
Is that my point? Versus
Uh,
what's the benefit of incorporating the computer vision model versus having a doctor and the variability in the human error that you
Well,
have?
it is a problem of if so the benefits comes from it can save the doctor's time to maybe do more examining and to think about the image to to do research on to compare it with previous examples and make the decision. So if you narrow down to two cases, then okay, maybe I can just revisit the historical diagnosis of these two example cases because it already excludes many other possibilities for me. And for the computer vision system, how it works on this diagnosis is that it will give a prediction
Mm-hmm.
of probability of each class and report the highest ones.
Yeah, so the doctor will use that and say, okay,
Yes.
I need to verify that, computer's classifying this at 88%.
Yeah.
This is consistent with my experience, okay? And the other concept is that the availability of deployment of those decisions. I'm thinking of a specific example of the deployment of a model that identifies hip dysplasia in babies in rural areas in Chile. So you can take the X-ray there in a rural area in Chile, but you don't have the doctor, the specialist to review it, and they have to send it and they have to review it.
Yeah.
So the other advantage, the economical advantage, is can you deploy this in places that you didn't have before? So that's not a human time. You're not making a task more efficient, but actually you're making it more available.
Yes. Yes. So this is like creating new values because of the deployment of the system. Yes. So you may say that if we are considering more benefits, then we are underestimating the use of the system.
That's another way to say.
So any questions from the Zoom folks? Okay, so if no, I would thank you for your participation, and I received many good suggestions and feedbacks. Thank you so much for your involvement. Thank you.